morning we're looking at, we want to find a way to describe a vector space. Well, the idea behind that is we just try to find a minimal set that describes every single vector in the vector space. The notion of spanning. You have n vectors, call them v1 to vn. Any linear combination, or any sum of that form is called a linear combination of your v's. Right? The set of all linear combinations is called the span of those vectors. It'll be notated span of the set. As it turns out, this set is a subspace. Specifically, it's a subspace of the vector space you got the vectors out of. That's not too difficult to show. This brings into notion a spanning set. A set of vectors is a spanning set for your vector space if and only if every vector in V can be written as a linear combination of V1, V2, Vn. We also say that that set spans your vector space. Yeah. So if we know that a set, let's call it S, spans a vector space V, every single vector in V can be gotten from the vectors in S. The idea now comes down to, well, that's great, but is that a minimal set? So is that the minimum number of vectors we would need? We'll be looking at that shortly. If vectors v1 through vn span a vector space V, and one of the vectors can be written as a linear combination of the other n-1 vectors, then those n-1 vectors span V. Okay. So you have a set of vectors that you know span your vector space, and one of the vectors is a linear combination of the others. Then you can just remove that vector from the set and you still have a spanning set. Well, that would mean in that case that is not a minimal set, is it? If you can remove it, it's redundant, you don't need it, so it's not minimal. So it seemed the idea would be, right? You know that a set spans your vector space. Now just check to see if any of those vectors in that set are a linear combination of the others. If it is, remove it. You don't need it, it's redundant. Given n vectors, v1 to vn, it is possible to write one vector, or one of the vectors, as a linear combination of the other n-1 vectors if and only if there exists scalars c1 through cn, not all of which are 0, such that c1 v1 plus c2 v2 plus blah 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 is the 0 vector. In other words, this is a system of equations, right? The system of linear equations. Specifically, a system of homogeneous linear equations. Well, one of the vectors would be a linear combination of the other ones whenever this system has non-trivial solution. Right? That's what it means for not all the scalars to be 0.
C1, C2, etc. are real numbers, right?
Yeah, they're just some of the constants. Right? For our purposes, real numbers. In general, any number for the field that you're working in. So then what we would do is once we have our spanning set, we'd set up that system and see if there's a non-trivial solution. If there is, then we know that at least one of the vectors is a linear combination of the others, thus it's not a minimal spanning set. Then we just have to figure out, okay, which ones do we remove? If you only get trivial solutions, you're golden. Right? Because that says, oh, look, we got a trivial solution, so none of the vectors are linear combinations of the others.
I'm a little slow. Could you just quickly define trivial solution for me?
All the C's would be 0.
Okay. Thank you.
That's the only solution that's trivial.
What's the application of like having a minimal set? Like, what does that do?
It's the smallest set that would perfectly describe the vector space. Just so we don't have to worry about writing out every single vector in the vector space, we can just go, this set here describes this vector space.
So, like in essence, you could be given like a couple vectors, and then that will just describe the vector
Perfect,
space.
right? Because you can get every other vector just from those. Right. I'll actually define what that set is called. That set has a name on Thursday. This is leading up to the foundations of that.
So would you be using like actual numbers to solve this kind of stuff, not like last Tuesday, where you just like
Yeah. So these would be you want to find. So the C1, C2, Cn, you want to make sure that they're all zeros. Right. And obviously, each of the vectors would be a vector from the vector space. Now, the problem is if it's an abstract vector space, they may not be numbers. But for the most part, we're going to be sticking with some concrete, so Rn, right, which are the vectors from physics that you're used to from calculus as well. Polynomials we'll deal with. Matrices we'll be dealing with.
All right.
Yeah, R to the n space. Ordered n tuples. Right, so R2 would be a set of ordered pairs. R3 is a set of ordered triples, X, Y, Z.
Oh, yeah.
That's what Rn is, except we write them as vectors instead of an ordered n tuple. For this purpose, we define what it means for a set to be linearly independent. And it's just the system has only the trivial solution.
Is this different than the linear independence that we study with matrices, or is this the same thing?
Same thing. It's covered in the text with matrices. It really shouldn't be. I think they specifically stuck with Rn, whereas now it's going to be expanded to any vector space. If they're not linearly independent, we just say that they're linearly dependent. So our goal ultimately will be to find a linearly independent spanning set. We call that, for now, we're going to call it a minimal spanning set. We'll call it something else starting on Thursday. So for the most part today, we're just going to be focused on deciding whether a set of vectors would span a vector space and whether they're linearly independent.
We must have put this up last Tuesday, like other than like just getting the basics of what a vector space is.
To define what a vector space is. That was
So like what are the 10 principles ever used in anything, or is that just like just defining what a vector space is?
so they're used in theory, right? So once we start to prove things with vector spaces, we use them. Right? So we know that because it's a vector space, it has to satisfy those 10 axioms, and we use that to our advantage, like we did with subspaces. So if you go back, if you watch the video that's posted for subspaces, remember we said, oh, we don't actually have to show all 10 axioms, just show 3 things. Right? It contains the identity, it's closed under addition and closed under multiplication. Right? You can actually prove that because V is a vector space and satisfies all 10 of those axioms, a subset would also automatically satisfy all those axioms if it's closed under addition and multiplication. So it's things like that. But other than that, outside of theory, they're not really used. It's just saying, here's what it is.
So like more advanced like proofs, I guess.
Yeah, so when you start, it's really, so algebra is a weird topic because algebra is actually just very abstract in general and doesn't have a lot of applications, let's say, no physical applications. It's more just the study of structures.
Well, algebra 1 and 2.
Algebra 1 and 2 is actually just a special case of algebra. Specifically, it's a special case of field theory, which is studied in, it's called modern algebra in undergrad, but it's abstract algebra. But that's what algebra really is. It's just the study of structures. the most basic of all structures is a group, which you study in abstract algebra. Yeah, so it's very weird. You've been lied to your whole life.
But isn't like calculus based on like algebra essentially?
Calculus uses algebra, it's not really based on it. Calculus is a different branch of mathematics known as analysis. So whenever, do you remember in Calc 2 when you were studying numerical integration?
Yeah.
No analytic antiderivative? That's where the term analytic comes from. Calculus is analysis. So whenever you think of analytic, you're thinking of calculus. Let V1 through Vn be vectors in a vector space V. Any vector V that is in the span of those n vectors can be written uniquely as a linear combination of V1 through Vn if and only if they are linearly independent.
So is the linear combination the same thing using Calc 3? Like when you're first introduced to vectors?
So I'm not sure when the term linear combination comes up in Calc 3, but a linear combination is, all a linear combination is a scalar times a component, so in this case a vector, plus a scalar times the other vector, plus a scalar times another vector. That would be a linear combination. So I'm not familiar with when it's introduced in Calc 3, so I don't use that terminology in Calc 3.
It's the very beginning when you're just defining what a vector is, and then my teacher went over like linear combinations. I forget what the application was for though.
Yes, I'm not familiar because I don't ever use that terminology. It probably does appear in Calc 3. I know it does actually. When you do sum of forces, for instance, that's a linear combination. Right? All the scalars happen to be 1, you're summing up the forces. Linear combinations are used all the time. Even if you just do 2 plus 2, that's a linear combination. Right, so what this is saying is, let's say you have a set of vectors that linearly dependent. Well, then any vector is the linear combination is not unique. Right? You could theoretically write a vector as a linear combination multiple ways. Only if it's linearly independent is there only one set of C, of C1, C2, Cn that would make it a linear combination. So if you think back to the unit standard, the standard unit vectors, I hat, j hat, k hat, they're actually linearly independent, and they span R3. Right? Every vector can be written as a unique linear combination of I hat, j hat, k hat. Right? That's an application now right out of calculating physics. And that linear combination is actually very easy to find, right? 5, 8, 2. That's a 3 vector. What are your scalars to write as a linear combination?
It would be their LCM, right?
5, 8, and 2, right? You write as 5i plus 8j plus 2k.
Oh, yeah.
5 is C1, 8 is C2, 2 is C3. Those will be your constants. And those are actually also play a role later as well. We call them coordinates. We'll also be studying that. We're going to show that R3 is spanned by these three vectors. Now keep in mind that I just gave you the standard unit vectors, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, that's I hat, j hat, k hat. They span R3. But a spanning set is not unique. And theoretically, you can have an infinite number of sets that would span R3. They do have to have something common. We'll get into what that thing is. But I'll tell you, it has to be a set of three vectors. You can't have less and you can't have more. Well, you can't have more to be a spanning set, but not a minimal spanning set. Minimal spanning set of R3 would have to contain three vectors. So we're going to show that these would also span R3. So we could represent every three vector as a linear combination of these three. Again, what is it? I just said it. What does it mean to span R3? Given any three vector, it can be written as a linear combination of these three vectors. So, pick an arbitrary three vector. Call it ABC. What we need to do is we need to show that there are three real numbers, C1, C2, and C3, such that C1 times U1 plus C2 times U2 plus C3 times U3 is equal to that vector ABC. Once we show that there are three scalars, we're done. We've shown that it spans. So the goal now is to find those three scalars. Right, so come up with a rule for those three scalars. Well, A, B, and C are just arbitrarily chosen real numbers, right? That's a system of linear equations. Specifically, that's going to be a system of three equations and three unknowns. What are your unknowns? C1, C2, and C3. How do we solve systems of equations?
Well, if it's a matrix, you could do RDF.
What's that method called?
Gauss-Jordan elimination?
Reduction.
Reduction.
Gauss-Jordan reduction. Let's do that. What I'm going to do for this problem is I'm going to explicitly go step by step and show you how to set up the matrix. Show you why that's the setup. I won't be doing that in the future. We'll go right to it. So write this equation as an actual system. That would be your first equation, right? C1 plus C2 plus C3 is A. Second equation in the system. C1 plus 2C2 plus 5C3 equals B. The third equation, C1 plus 3C2 plus 8C3 equals C, right? That is our system. Now we're going to explicitly write everything out. So look at that system. What is our coefficient matrix?
Going by row 1, 1, 1. Do you include the A?
That's not in the coefficient, that's the augmented. I just want the coefficient for right now.
And then the next row would be 1, 2, 5, and then 1, 3, 8.
What would our constant vector be? And then obviously the vector of unknowns. X hat, right? I actually have room. Let's do this.
Would it be wrong to make ABC 0? Because, like, it's supposed to have one unique solution that's equal to 0.
In this case, no, we don't want A, B, and C to be 0.
But if it, like, specifically asks, like, is this...
If you're looking for is the specific vector in the span, then you just use that specific vector, yes. But right now we're trying to show that this is going to be true for any vector. So we can't just use 0, 0, 0. That's only one example. Doesn't necessarily prove it spans. So I want to take a look at these right now. Look at the first column of A. What does it look like?
So, it's U1.
What about the second column of A?
It's U2.
And the third column?
U3.
And B hat? It's just our arbitrarily chosen vector, right? It's called blue. Oh. Now I know how to skip the step. You just set up your matrix where each column is one of the vectors. And ultimately, it's going to be augmented with your B, right? The one you're trying to write as a linear combination. Augmented with ABC. Question? Do I want to do this by hand or not?
Well, you can't use a calculator, right? Because there's variables.
Yes, you can. If
Well,
you
it's
have,
an inspire. Yeah.
if you have the CAS version, you can. Calculate on this time. I'll just use a calculator, I think. Semicolon. 1, 2, 5, 8. Semicolon. 1, 3, 8. There's your RREF. Which I'll let you verify by hand.
I'm not quite grasping what exactly span is, but what would it be in like other words?
It's just, so we say that a set spans, meaning that every single vector in the vector space is a linear combination of that set of vectors. Right? So in this case, if you look at this, this here would be our answer for C1, right? Remember, A, B, and C are just real numbers, right? They're scalars. This would be our answer for C2. This would be our answer for C3. So these are the scalars that we would need to be able to write A, B, C as a linear combination of 1, 1, 1, 1, 2, 3, 1, 5, 8. So the vector ABC would be this number times 1, 1, 1 plus this number times 1, 2, 3 plus this number times 1, 5, 8. Right, so just by choosing appropriate scalars, we can write any free vector just from these three. Again, the easiest way to think about it would be the I hat, J hat, K hat in terms of what we're doing. We found our C1, our C2, and our C3. That means we showed that such scalars exist, which is precisely what we wanted to show. What we could do now is I could give you an arbitrary 3 vector. And I could say find your constants. Let's come up with one. Do 2, 3, 5. Let's do the first 3 prime numbers. 2, 3, 5. Find your scalar C1, C2, C3, such that 2, 3, 5 is a linear combination of those three.
What's the point of regular span versus like the, what was it, the
Minimal
least-
span?
Yeah, minimal span.
Because we want to be able to describe the vector space in as few vectors as possible. Right? It wouldn't make sense to have more vectors than you need, right? They're redundant vectors.
Well, like, what's the point of regular spanning versus, like, I feel like the practicality of minimal spanning, like, makes sense, but like, what does regular spanning do? Is there like any?
Also, all spanning just means is every vector is a linear combination of those vectors. Minimal spanning just means it's as few vectors as possible. Right? So regular isn't really a thing. It's still a spanning set. We just add minimal to show that these are the fewest number of vectors you need. Right? There's no redundancy, let's say. Right? So it's not minimal. Let's say there's a fourth vector in here. That fourth vector is a linear combination of the other three. Kind of defeats the purpose then, right? It's redundant. You don't need that fourth vector. So we get rid of it. Got -2 for C1. Five for C2. -1 for C3. That would be our linear combination of three vectors.
What did you say C1 was again?
-2. Oh wait, why can't you see that? Oh, I already fixed that. And as I said, those scalars, so let me write this as plus -1, will be important a little bit later.
If we are given a question like this on a test, how do you want us to format the answer? Do you want it like that?
Well, it depends on what I'm asking for.
If you give us, what were you asking for this question?
Well, this question was to prove that it spans.
Yeah.
So that would be what I would need. I wouldn't need to see the system.
Just the raw, okay.
Yeah, I would need to see the matrix, your row reducing it, and its interpretation.
Okay.
And as well as like an explanation on why we're doing it. And that's fine. If I was asking for write this as a linear combination of these three vectors, set up the augmented matrix, except put the actual values of A, B, and C in, or reduce it, and then use those constants to write it just like that. Find conditions on A, B, and C so that the vector ABC is in the span of 1, 2, 0, negative 1, 1, 2, and 3, 0, negative 4. So let's go ahead and suppose that that is the case. Then we have three real numbers.
Can we just look at it and say it's not?
How do you know it's not?
Because the third number has to be even. So C has to be even then?
Well, that's what this is asking, right? Find conditions that would make it in the span.
So, okay, C, yeah, okay, I got you.
That's why I'm saying suppose it is.
Okay.
We're now going to find, okay, then what conditions we have to have on A, B, and C. And so if we're supposing it's in the span, that means that there are three real numbers, so that we can write this. At this point, just jump right to the augmented matrix. First column, 1, 2, 0. Second column, negative 1, 1, 2. Third column, 3, 0, and negative 4. By the way, C wouldn't have to necessarily be even, because you forgot that those are any real numbers. So I could just say C2 is a half, C3 is 0, and I have 1. But there are conditions that are going to be satisfied. Got the augment. A, B, and C. Let's just take a look at what happens if we throw this into a calculator. And I'm going to choose the easy way. Ah, yeah, can't see it. That's not really helpful. Notice that yellow exclamation. Where's my arrow? That came up. That's just saying that the domain probably changed. And so you can just ignore it. That last row, 0 equals 1. Oh dear. But you have to remember that's because it's zeroed out the real numbers A, B, and C. We have to do this by hand to actually get a usable result. So let's get started. The negative 2 row 1 plus row 2, right? That'd be 3, negative 6. We get A, negative 2A plus B. I'm not even going to bother trying to make that 3 or 1. Multiply by 2, negative 2/3, right? And add to row 3. And notice what you're going to get. Negative 2/3 times negative 6 is not 4. Four thirds A minus 2/3 B plus C there. And don't like that fraction. So just go ahead and multiply row 3 by 3. We can stop. We have our condition. In order to have this in the span, we can't have that last row be 0 equals something other than 0, right? Otherwise the system would be inconsistent. So that 4A minus 2B plus 3C had better be 0 to be consistent. There's the condition. So any 3 vector that satisfies that condition would be in the span of these 3 vectors. So what can you say? Does this set span all of R3? No. It spans a specific subset of R3, but not all of R3. Let S be a subset of V. Prove that if W is a subspace of V containing S, then the span of S is a subset of W. Right, so let's say that we have a set of vectors u1 to un that are in S. Well, then each of those u's must also be in W. Why? Because why do I know that if those u's are in S, they must also be in W?
Because it's a subset.
Hmm?
Because it's a subset.
Mm-hmm. What symbol? That's talking about this one here.
No, it's a subset. Yeah.
That's subset. Yeah, it says W contains S. That is written this way. It's not very commonly used in set theory. But it's kind of like the greater than equal to versus less than equal to. Same kind of idea. So W contains S, which means S is contained in W, or S is a subset of W. We're also told that W is a subspace, right? Oh, I used K in my notes, not N, whatever, it doesn't matter. So, since W is subspace, every possible linear combination of the vectors has to also be W, right? Because W is closed under multiplication and addition. On the other hand, sorry, not S. That has to be true. Right, because that's the definition of span S, right? All linear combinations of the vectors in S. Which means that span S has to be a subset of W. Are they linearly independent? So what does it mean to be linearly independent? That system has to have only the trivial solution. So let's set up the system. So I'm not going to go through the argument again, but from the same arguments we did for span, we can immediately jump to the augmented matrix, right? Actually, I don't need to worry about setting that up. Right, because I believe we mentioned that homogeneous system will have non-trivial solution if and only if it doesn't reduce the identity. Something along those lines. The coefficient matrix. You could also use determinants. Right, well, the determinant had to be 0 to have a unique solution. I'm just going to set it up this way for now. Notice that no matter what we do, that's always going to be augmented with 0, 0, 0, right? Which is why in the future I'm not going to write that. I'm just going to write the coefficient matrix and see if we can get it down to the identity or not. Again, for this problem, I will stick with it. 1, 2, 4, 0. Next row. 1, 3, 5, 0. Next row. 2, 1, 5, 0. Should be 2150, right? Because it was 455.
Yeah.
And again, I'm going to explain this out, but generally speaking, it doesn't reduce the identity, so you're done. It's linearly dependent. But here's why. This would say that C1 plus 2C3 equals 0, and C2 plus C3 equals 0, which means C3 is a free variable. That means we have a non-trivial solution. Let C3 be 1. You have a non-trivial solution. So they have to be literally dependent. Suppose that U, V, and W are linearly independent. We're going to show that U plus V, U minus V, U minus 2V plus W are also linearly independent. So what we want to show is that that system has only the trivial solution. And i.e. C1, C2, C3 are all 0. Group all of your C's together. So for C1, I'm sorry, group all of your vectors together. So all of the U's, all of the V's, and all of the W's. So U, C1 plus C2 plus C3 plus C1 minus C2 plus, minus 2C3. And for W, it's just plus C3W, right? shut up the rest of about 5 minutes. But we're told that u, v, and w are linearly independent, right? So that means that any constant times u plus any constant times v plus any constant times w equal to 0 can only have the trivial solution. Well, what was the constant for u? C1 plus C2 plus C3, right? That has to be 0. And what's the constant for v? C1 minus C2 minus 2C3? That has to be 0. And C3 has to be 0. What's the coefficient matrix of that system?
One, by row. 1, 1, 1, 1. And yeah, an extra one. 1, -1, -2, 0, 0, 0.
What did you say the last one was?
0, 0, 1.
It's going to suffice to show that this reduces down to the identity.
Are we just assuming that based on like work we didn't do that it would?
Well, there's a theorem that says that it's going to be trivial solution if and only if the coefficient matrix reduces down to the identity. Right? Because we're dealing with homogeneous systems.
What I mean is that like we're assuming that we did the work to prove that it was an identity matrix.
I haven't done it yet. I'm just going to now reduce this.
Oh.
Now I'm out of time. That's fine. I'll just do the calculator real quick. Boom, identity. C1, C2, and C3 all have to be 0. The homework 11 is due Thursday. There are 2 homeworks for this stuff, one on span, one on linear independence. So that's homework 12 and 13. They will not be due next Tuesday. They are due the Tuesday after that. Because next week is spring break. We study, or we look at the basis on Thursday.
I'm sorry. I'll send you.
Yeah.